Okay, I want to start talking about inclined planes by talking about two watermelons. Here's a watermelon that's just sitting on the ground, and here's a watermelon that's falling towards the ground. Now, if we were to draw the forces that are acting on these two watermelons, obviously we would draw a weight force and draw a normal reaction force. So this watermelon sitting on the ground, here's the weight force, and the normal reaction force, since it's not going anywhere, will be equal to and opposite the weight force. Of course, they're not action-reaction pairs, but they are equal and opposite. The falling watermelon, however, will have the same weight force, but it's hitting the ground with a lot more force, and so the normal reaction force there would be considerably larger and will cause quite a mess. So the point I'm making here is that the normal reaction force and the weight force are not action-reaction pairs. They're not equal and opposite, even though they often are, such as in this case. They don't have to be equal and opposite. So this is important when we consider an inclined plane. Normally when a body's at rest on a horizontal plane, as we saw with the first watermelon, the normal and the weight force are equal and opposite, but they don't have to be. They don't need to be. So here is an object, it could be anything sitting on an inclined plane at an angle theta, and if we were to draw the forces acting on this, we would draw a weight force down, mg, and there would be a normal reaction force, but the normal reaction force is always at right angles to the plane. So it's always perpendicular, it's always at a normal. That's why it's called the normal, is because it's at right angles to the plane. So there's the normal. So what we're interested in is the components of this weight force that act parallel to the slope and perpendicular to the slope. Because it's this force, this component of the weight force that acts down the slope that pulls the object down the slope. So what we're going to do is some more trigonometry and break this weight force up into two components, into a right angle triangle. Now importantly, this angle down here, this theta, is this same angle here. So I can label that theta there. So I'll draw it a bit larger over here. So we get the hypotenuse, there is theta, there's the right angle, this side here is mg, and so this weight force down here is the net force. So this side here, this opposite side, by trigonometry we can say that this side, we'll call this f, parallel to the slope, and this side force perpendicular to the slope. So we can say that the force parallel to the slope by trigonometry is mg sine theta, just by looking at this little right angle triangle here, and the force perpendicular to the slope is mg cos theta. This is a really important diagram for you to have a copy of on your cheat sheet. So what we get is a triangle like this. So the force down the slope, this pulling down the slope, is equal to mg sine theta. The force normal to the slope, mg cos theta. So this is the normal force, and this is what's pulling down the slope, causing the object to move. Now, a special case of this is when there is constant velocity, or when there is no velocity, because in those cases acceleration is zero, and by Newton's second law, when acceleration is zero, net force is zero. So that means all the forces are balanced. So that means that the force pulling an object down the slope must be exactly matched by a force pushing it up the slope. So that is normally a frictional force. It could be some sort of string holding it up, but it's normally a friction holding that object on there. call it FR for friction up there. And so what that means is that we can work out the value of friction is equal and opposite to this weight force pulling it down the slope. So the friction here is, I guess we could say, the negative of mg sine theta. If we're considering mg sine theta to be positive, we're taking this direction down the slope as positive, then the frictional force will be opposed to that in the opposite direction. Now this, of course, happens both when the object is stationary on the curve, when it's just sitting there. It also occurs when it's moving at a constant speed down the slope. Because remember, by Newton's first law, an object will continue in motion unless acted on by an unbalanced force. So a skier moving down a slope at a constant speed will have a weight component down the slope, mg sine theta, equal to the frictional force pushing them back up the slope. So this is both when velocity is 0, an object's at rest on a slope, or with constant velocity.